The vast, dark, and cold space between the orbits of Mars and Jupiter houses a fascinating world that has challenged, and still challenges, our understanding of the solar system's architecture for over 2 centuries. This is Ceres, the largest object in the main asteroid belt and the only dwarf planet located in the inner solar system. The history of Ceres did not begin through the lenses of a telescope, but rather on the pages of mathematical calculations. At the end of the 18th century, European astronomy was dominated by a hypothesis known as the Titius-Bode law. Johann Daniel Titius, a German astronomer and professor, and Johann Alert Bode, director of the renowned Berlin Observatory, popularized an empirical formula that described the distances of known planets from the Sun. The arithmetic rule was relatively simple. Start with a numerical sequence 0, 3, 6, 12, 24, and so on, always doubling the value at each step. Add the number 4 to each of these values and then divide the final result by 10. This mathematical proportion predicted with frightening accuracy the orbits of Mercury, Venus, Earth, Mars, Jupiter, and Saturn. However, it left a glaring gap. The law dictated that there should be a missing planet at approximately 260 million miles from the Sun, or about 2.8 times the distance between the Earth and our star. The faith in this mathematical symmetry was so absolute at the time that astronomers were certain an invisible planet was out there, just waiting to be discovered. To find this phantom world, the Hungarian astronomer Baron Franz Xaver von Zach organized, in the year 1800, an international group of 24 elite astronomers. They called themselves the Celestial Police. The working method of the Celestial Police was to divide the zodiac, the band of the sky through which the Sun, the Moon, and the planets apparently transit, into 24 equal sectors. Each astronomer would be responsible for meticulously sweeping their slice of the cosmos every night. The importance of this organization lies in the fact that it was one of the first truly collaborative and international scientific efforts in modern history. Ironically, the great discovery did not come from the prestigious Celestial Police. On the 1st of January, 1801, the very first day of the 19th century, Giuseppe Piazzi was working alone. Piazzi was a Catholic monk of the Theatine order, a mathematician, and a brilliant astronomer, founder of the Palermo Astronomical Observatory, located on the island of Sicily, in the extreme south of Italy. Piazzi was methodically measuring the exact positions of stars to update a star catalog when he noticed a small point of light moving slowly against the motionless background of stars over several nights. Piazzi, demonstrating extreme scientific rigor, initially published his discovery as a comet, although he noted in letters to colleagues that the object's movement did not show the cloudiness or the tail characteristic of these bodies of vaporized ice. Piazzi decided to name his discovery Ceres Ferdinandia. The name honored Ceres, the ancient Roman goddess of agriculture, harvests, grain, and maternal fertility. In Roman religion and mythology, the island of Sicily was considered the earthly home and the sacred domain of Ceres. By choosing this name, Piazzi not only paid tribute to the land where the observatory was built, but also helped solidify the astronomical tradition of using the Greco-Roman mythological pantheon to christen new celestial bodies. The term Ferdinandia was a tribute to King Ferdinand IV of Naples and Sicily, but this political part of the name was quickly discarded by the international astronomical community. Shortly after the discovery, a technical and mathematical problem of immense proportions arose. Piazzi managed to observe and record the position of Ceres for only 24 consecutive nights. In February of 1801, a severe illness prevented him from continuing his work. By the time he recovered and other astronomers received the news through slow letters, the Earth and Ceres had moved in their orbits. Ceres came too close to the Sun's glare from the Earth's perspective, becoming completely lost in the daylight. Scientists of the time did not possess the mathematical tools necessary to calculate a complete orbital trajectory and predict where Ceres would reappear in the night sky based on such a minuscule data sample. Less than 1% of the total orbit had been recorded. Ceres was lost. It was then that a 24-year-old German named Carl Friedrich Gauss stepped onto the stages of science. Gauss was already on his way to becoming what historians would call the prince of mathematicians. His importance to physics, statistical mathematics, and astronomy is fundamental to almost all modern science. To solve the celestial enigma of Ceres, Gauss developed a revolutionary mathematical technique that we use to this day, called the method of least squares. Instead of trying to force a single perfectly exact equation that would accommodate the inevitable small errors of observations made by 19th-century telescopes, Gauss's method stated that the most probable orbit would be the one in which the sum of the squares of the differences between the values observed by Piazzi and the mathematically calculated values was as small as possible. Armed with this brilliant analytical tool, Gauss deduced the orbit of Ceres and predicted where the celestial body would be at the end of that year. In December of 1801, Baron von Zach and astronomer Heinrich Olbers pointed their telescopes to the exact coordinates provided by Gauss's papers. Ceres was there, shining in the darkness, exactly where the brilliant new mathematics predicted it would be. The lost planet had been recovered. The initial euphoria of having found the lost planet between Mars and Jupiter lasted very little. In the year 1802, the German astronomer Heinrich Olbers, the same man who had helped confirm the orbit calculated by Gauss, discovered a second celestial body in the same region of space. He called it Pallas. The existence of two planets sharing essentially the same orbit was a scandal for the celestial mechanics of the time. To solve this conceptual anomaly, the brilliant German-British astronomer and composer William Herschel entered the debate. Herschel is one of the most titanic figures in the history of science, famous for having discovered the planet Uranus in 1781 and for having built the largest and most powerful telescopes of his era. By observing Ceres and Pallas through his lenses, Herschel noted that, unlike the classical planets that exhibited a sharp and round disk, these new objects appeared only as points of bright light, exactly like distant stars. Due to this visual appearance, Herschel coined a new term derived from Greek, asteroid, which literally means star-like. Between the years 1804 and 1807, two other bodies, Juno and Vesta, were discovered in the vicinity. Initially, the schools and universities of the 19th century taught that our solar system had 11 planets. However, as telescopes became more sophisticated in the 1850s, astronomers began to discover dozens, and then hundreds, of these small rocky bodies. It became scientifically untenable to classify all of them as planets. Thus, Ceres suffered its first great cosmic demotion. It was stripped of its planetary status and reclassified as Asteroid No. 1, becoming just the largest member of the newly named Asteroid Belt. But Ceres is fundamentally different from the misshapen chunks of rock that make up the rest of the belt. Its distinction lies in the relentless laws of physics, specifically in a principle known as hydrostatic equilibrium. The pull of gravity draws all mass toward the center of a body. When an object accumulates enough mass, its own gravitational pull becomes so overwhelming that it overcomes the structural resistance of the solid material that composes it, forcing the rock and ice to yield and mold themselves into the most efficient geometric shape possible, a sphere. The strength of this gravitational pull is governed by Isaac Newton's law of universal gravitation, which states that the gravitational force between two objects is equal to the gravitational constant multiplied by the mass of the first object and the mass of the second object, with all this result divided by the distance between their centers squared. With a diameter of approximately 584 miles and a colossal mass that adds up to almost 1/3 of the entire weight of the asteroid belt, Ceres has enough gravity to have molded itself into a perfect sphere over eons. It was this exact physical characteristic that led the International Astronomical Union, in the historic and controversial Congress of the year 2006, to reclassify Ceres once again. It was elevated to the newly created category of dwarf planet, the same status granted to Pluto. To understand how Ceres acquired this mass and shape, we must travel back in time, about 4.6 billion years ago, to the genesis of our solar system. It all began in a vast and cold spinning cloud of hydrogen gas, helium, and stardust known as the solar nebula. As gravity caused the center of this nebula to collapse to ignite our primitive sun, the remaining material formed a flattened disk of dust around the young star. Through a process called planetary accretion, microscopic grains of dust collided and stuck to each other due to electrostatic forces, forming small pebbles. These pebbles clumped together to form larger rocks, which in turn collided to form massive bodies hundreds of miles in diameter, called planetesimals. Ceres is a living fossil of this turbulent era. It is classified by astrophysicists as an intact planetary embryo. It began the exact same growth process that eventually generated Earth, Mars, and Venus. However, Ceres's growth was violently interrupted. The culprit for this planetary abortion was the immense gravitational influence of the gas giant Jupiter. Jupiter, possessing more than twice the mass of all the other planets combined, exerted massive gravitational perturbations. Jupiter's gravity stirred the primitive asteroid belt, accelerating Ceres's neighboring planetesimals to incredible speeds. Instead of gently merging into a giant planet when they met, these bodies began to collide with cataclysmic forces, shattering into smaller fragments. Ceres survived this cosmic shooting gallery but was deprived of the building material necessary to grow into a full-sized planet. The exact location where Ceres formed also dictated its internal chemistry. Astronomers believe Ceres originated beyond what we call the solar system's snowline. The snowline is the thermal boundary around a star where temperatures drop enough for volatile compounds, such as water, ammonia, and methane, to freeze into solid ice grains. If Ceres had formed closer to the Sun, the intense heat would have vaporized the water, leaving only dry rocks and metals, as we see on Mercury or Venus. Because it clumped together in the dark cold beyond this snowline, Ceres incorporated vast amounts of water ice into its initial structure. The global density of Ceres reinforces this. Density, which physically is equal to the total mass of an object divided by its volume, is about 135 pounds per cubic foot. This is a surprisingly low density compared to rocky planets like Earth. The math and chemistry behind this density suggest an astonishing fact. Water may make up to 25% of Ceres's total mass and half of its volume. This lonely little world harbors more reserves of frozen freshwater than all the freshwater contained in every lake, river, and sweet groundwater aquifer on our own planet Earth. For over 2 centuries after its discovery, Ceres remained a frustrating enigma, appearing in Earth's best telescopes merely as a pixelated blur. The true face of this world remained hidden until the year 2015, when humanity finally sent a robotic emissary to investigate. This was the Dawn mission, a space probe operated by the American Space Agency. The Dawn mission, as its name suggests, was designed to investigate the dawn of our solar system. The project was led by principal investigator Christopher Russell, a renowned American physicist and space scientist, whose importance lies in the fact that he was a pioneer in the study of magnetic fields around planets and moons. To reach Ceres, which lies far beyond the orbit of Mars, the Dawn spacecraft did not rely on the violent and short burn of traditional chemical rockets. Instead, it utilized revolutionary ion propulsion. The engineering and physics behind the ion engine are elegant and based on fundamental principles. Instead of using fire, the probe uses electricity generated by its massive solar panels to electrically charge a heavy noble gas called xenon. By removing an electron from the xenon atoms, the gas acquires a positive electrical charge, becoming an ion. The probe then uses a strong electric field to accelerate and expel these ions out the back of the engine at astonishing speeds, reaching over 86,000 miles per hour. The spacecraft's movement is governed by Newton's third law of motion, which dictates that, for every action, there is an equal and opposite reaction. Although the thrust of each individual ion is minuscule, similar to the weight of a sheet of paper resting on your hand, in the vacuum of space, where there is no friction, this continuous acceleration over months and years allows the ship to reach monumental speeds. When the Dawn probe finally entered Ceres's orbit in March 2015, the images it sent back to Earth shocked the astronomical scientific community. Instead of a dead and monotonous asteroid, the spacecraft revealed an active world, marked by glaring anomalies. The most spectacular and immediate feature was a set of intensely bright spots that reflected the sun's light with a blinding intensity, located on the dark floor of an immense impact basin. This giant impact crater was named Occator Crater. In ancient Roman religion and mythology, Occator was a minor deity linked to agriculture, being one of the helper gods directly subordinate to the goddess Ceres. His specific function in the pantheon was to preside over harrowing and the act of plowing the land, preparing the soil for planting. Roman religion was extremely pragmatic and compartmentalized. Having specific gods for every millimeter step of cultivation demonstrates the absolute and existential importance of agriculture for the maintenance and expansion of the Roman Empire. The International Astronomical Union maintained this tradition, naming the craters of Ceres after agricultural deities from cultures across the earthly globe. The brightness at the bottom of the Occator crater was not snow, as some initially suspected. The analysis from the instruments aboard the probe revealed the exact chemistry of those spots. They were formed by sodium carbonate, a type of salt. On our planet, we find large concentrations of sodium carbonate in deep ocean hydrothermal environments or in highly salty alkaline lakes, environments where hot liquid water actively interacts with mineral rocks. The discovery of this material on the bare and frozen surface of Ceres confirmed an extraordinary theory. Salty liquid water, originating from a deep underground ocean, found an escape route through cracks in the crust generated by the asteroid impact that formed the crater. When this pressurized brine reached the surface devoid of atmospheric pressure, the water instantly evaporated into space, leaving behind a vast deposit of bright white salts. Even more surprising was the discovery of Ahuna Mons, a solitary and imposing mountain about 13,000 feet high, rising isolated on the cratered plains of Ceres. Planetary geologists soon realized that Ahuna Mons was not a common mountain formed by tectonic plates, nor a traditional volcano. It was a cryovolcano, an ice volcano. The physical mechanism of cryovolcanism differs drastically from terrestrial volcanism. On Earth, internal heat melts silicate rock, decreasing its density and causing magma to rise. On Ceres, the magma is a thick mud composed of frozen water, salts, and minerals. Thermodynamics and the unique physical properties of water drive this process. The physical rule tells us that density is equal to mass divided by volume. Water is one of the rare substances in the universe that expands when it freezes. Its volume increases, which means its density decreases. As the pockets of muddy and salty water freeze in the icy depths of Ceres, the physical expansion of the ice generates colossal internal pressure, forcing the viscous material upward through the crust until it slowly erupts, piling up into gigantic domes on the surface at temperatures of -148 degrees Fahrenheit. As if ice volcanism and underground oceans were not enough, the Dawn mission made a fundamental discovery in the Ernetet crater. The crater was named after the ancient Egyptian goddess of harvest and sustenance, often depicted as a cobra snake, who protected the fertile grains along the Nile River. Around this crater, spectrometers detected unmistakable signatures of aliphatic organic compounds. In chemistry, organic compounds are molecules built on extensive chains of carbon atoms, which serve as the essential building blocks for organic cellular biology. Ceres did not just have water, internal heat, and minerals. It also had basic organic chemistry, gathering the primordial ingredients for the possible emergence of life. The surface of Ceres, riddled with craters and dotted with bright salts, is merely the shell of a much deeper mystery. To truly understand the history and evolution of this dwarf planet, scientists needed to look beyond the rocky and icy crust, plunging into the darkness of its interior. But how can we probe the bowels of an alien world located hundreds of millions of miles away, without ever landing or drilling into its soil? The answer lies in one of the most elegant applications of astrophysics: gravitational mapping. During the final months of the Dawn mission, flight engineers lowered the spacecraft's orbit to a mere 22 miles above the dwarf planet's surface. At this extreme altitude, the probe became incredibly sensitive to microscopic variations in the density of Ceres's interior. As the ship orbited, areas of greater subterranean mass exerted a slightly stronger gravitational pull, accelerating the probe almost imperceptibly. Areas with less mass allowed the probe to decelerate. To measure these speed variations with surgical precision, scientists on Earth, led by researchers such as planetary geophysicist Carol Raymond, utilized the Doppler effect. The Austrian physicist Christian Doppler proposed this phenomenon in 1842. The Doppler effect is the change in the observed frequency of a physical wave when the source of the wave is in motion relative to the observer. If the probe accelerated toward Earth due to a gravitational anomaly on Ceres, the radio waves it transmitted were compressed, resulting in an increase in the signal's frequency. If the probe decelerated or moved slightly away, the radio waves were stretched, decreasing the frequency. By monitoring these infinitesimal changes in the radio signal over months, computers on Earth managed to build a three-dimensional map of Ceres's interior. The internal model revealed by the gravity data was fascinating. Ceres is not a homogeneous block of rock, but rather a differentiated body, structured in distinct layers, just like Earth. At the center, there is a dense core composed of iron-rich rocks and silicate minerals. Surrounding this dense core, there is a vast mantle that astronomers believe is not made of pure ice, but of a thick, viscous mud, a complex soup of frozen water, concentrated salts, and rocky dust. Above this thick mantle lies the solid and porous crust we see from space, a shell 25 miles thick composed of rocks, ice, and mineral deposits. The great revelation of this geological structure is that, in the past, Ceres's mantle was entirely liquid. Ceres was, billions of years ago, a global ocean world, covered by an underground sea of warm, muddy water. But unlike famous moons such as Europa, which orbits Jupiter, or Enceladus, which orbits Saturn, Ceres does not have a giant planet by its side to generate internal heat through friction and the force of gravitational tides. Ceres is alone in the freezing vacuum. So, how did this small world manage to generate enough heat to melt the ice and maintain an underground ocean for so long? The answer takes us to the realms of nuclear physics and the beginning of the universe. When Ceres formed from the primordial solar nebula, it incorporated long-lived radioactive elements, such as the unstable isotopes of potassium, uranium, and thorium. Deep within the dwarf planet's rocky core, these isotopes undergo a natural process of radioactive decay. The mathematics that govern the conversion of this decay into heat is dictated by the mass-energy equivalence law, established by theoretical physicist Albert Einstein in the year 1905. The fundamental equation of special relativity dictates that energy equals mass multiplied by the speed of light squared. What this means in planetary practice is that when the unstable atomic nuclei of uranium and thorium break apart inside Ceres, a microscopic amount of physical mass is obliterated from existence and converted directly into a prodigious amount of kinetic and thermal energy. This radiogenic heat, warming from the bottom up over hundreds of millions of years, melted Ceres's internal ice, creating the vast ocean. As cosmic eras passed, the supply of radioactive elements became depleted, the internal heat diminished, and the lethal cold of space won the thermodynamic battle. The global ocean began to slowly freeze, thickening the crust and trapping isolated pockets of hypersaline water in the depths. These residual brines are the key to the recent ice volcanism we observe in the Occator Crater. Salt acts as a powerful antifreeze in the universe. If you add sodium chloride or, in the case of Ceres, sodium carbonate and ammonium chloride to water, the freezing point of the liquid drops drastically. Instead of freezing at 32 degrees Fahrenheit, water mixed with these dense salts can remain in a liquid state at an impressive -40 degrees Fahrenheit. It is this muddy and extremely cold brine that still flows in Ceres's underworld, occasionally bubbling to the surface through recent geological fractures, keeping the heart of this ancient world faintly beating. The mythological symbolism is striking. In antiquity, the Roman goddess Ceres was intrinsically linked to the goddess Proserpina, her daughter, who was taken to the dark underworld by the god Pluto. Mythology dictated that the fertility of the Earth's surface was directly connected to what happened in the darkness of the subterranean world. Modern science has proven that the Romans, through their religious metaphors, were not entirely wrong. The bright and geologically rich surface of the asteroid Ceres is, in fact, the direct result of the complex chemistry and hidden oceans that simmer in the deep darkness of its interior. On November 1st of the year 2018, the historic Dawn mission reached its inevitable end. The probe completely exhausted its reserves of hydrazine, the chemical fuel used to control the orientation of its thrusters and keep its radio antenna pointed at Earth. Unable to communicate or align its solar panels to the Sun, the spacecraft plunged into an eternal silence. However, in a deliberate planetary protection effort, flight engineers ensured that the probe remained in a stable and perpetual orbit, where it will continue to circle Ceres for decades, or perhaps centuries, serving as a silver monument to human curiosity. The goal of this maneuver was to prevent the ship from colliding with the surface and contaminating the native organic compounds with terrestrial microbes carried from Earth. The silence of the Dawn probe, however, did not mark the end of our interest in the dwarf planet, but rather the beginning of a new era of ambitions. In the year 2022, the United States National Academies of Sciences, Engineering, and Medicine published the Planetary Science and Astrobiology Decadal Survey for the decade of 2023 to 2032. This extensive academic document is of paramount importance to the global scientific community, as it dictates the absolute research and funding priorities for the American Space Agency over a 10-year period. In this document, a Ceres sample return mission was listed as one of the highest-level priorities for the future of space exploration. The interest in returning to Ceres is motivated not only by the abstract pursuit of knowledge, but also by a strategic pragmatism essential for humanity's future among the stars. Ceres is widely considered by space architects as the ultimate oasis of the inner solar system. If we are to establish a permanent human presence on Mars or exploit the rich ore mines in the asteroid belt, Ceres offers the perfect location for a spaceport or a refueling station. Mathematics and physics support this grandiose logistical vision. The main advantage of Ceres lies in the escape velocity equation. In classical physics, escape velocity is defined mathematically by stating that the escape velocity is equal to the square root of 2 times the gravitational constant multiplied by the mass of the celestial body, with all this result divided by the radius of the celestial body. For a rocket to escape Earth's deep gravitational pull, it must reach a brutal escape velocity of approximately 25,000 miles per hour. This requires colossal rockets filled almost entirely with millions of pounds of fuel. In contrast, due to Ceres's low mass and small size, its escape velocity is a mere 1,100 miles per hour. Launching a ship from the surface of Ceres would require only a minuscule fraction of the energy and fuel compared to a launch from our planet. Furthermore, Ceres has the fuel itself in abundance beneath its crust. With vast reserves of frozen water, future robotic or human outposts could extract this ice and subject it to a chemical process called electrolysis. The chemistry of electrolysis dictates that 2 molecules of liquid water, when subjected to a strong electrical current, react and break apart to form 2 molecules of hydrogen gas and 1 molecule of oxygen gas. Liquid hydrogen and liquid oxygen are the most efficient and powerful chemical propellants known for modern rocket engines. Ceres is not just an easy stopping point, it is a self-sustaining cosmic gas station, brimming with water to drink, oxygen to breathe, and fuel for travel. But what about the long-term fate of the dwarf planet itself? When speculating about the future of Ceres on a cosmological timescale, we must look to the destiny of our own star. The Sun is a main sequence star that generates energy by fusing hydrogen into helium in its core. In approximately 5 billion years, the Sun will exhaust its hydrogen supply and undergo a catastrophic transformation, expanding to become a red giant star. The thermodynamic physics of this event will radically alter the architecture of the entire solar system. As the Sun's outer atmosphere swells and swallows the orbits of Mercury, Venus, and possibly Earth, the immense heat output will push the snowline, the boundary where ice can exist in a solid state, far beyond Jupiter. When this relentless wave of scorching heat reaches the asteroid belt, temperatures on Ceres will rise drastically. The protective crust of rock and dust will be heated. The ancient frozen underground oceans and vast ice mantles will begin to melt, and then, due to the lack of a dense atmospheric pressure to retain liquids, the water will enter a runaway sublimation process, violently passing from a solid state directly into a gaseous state. During this final and apocalyptic era, Ceres, the ancient Roman goddess of agriculture, will awaken from her icy slumber to put on a final spectacle. The dwarf planet will transform, for a brief period of time on a cosmic scale, into the largest and brightest comet in the inner solar system, ejecting colossal geysers of water vapor and developing a glowing tail millions of miles long. Eventually, under the gaze of a dying red sun, all of Ceres's organic water will boil away and disappear into the vacuum of space. What will remain will be only its dense iron and silicate core, a charred rocky fossil, silently marking the grave of the aquatic world that once held the secrets of planetary genesis and the dreams of human interstellar exploration.